Okay, so hi guys. So my name is Calvet, this is Pierre-Marc Bureau. We are going to talk about Switzer today. You have maybe already heard about Switzer because that's an hardware family that already exists for a long time now. So this presentation is really going to focus on the obfuscation of Switzer and the way we attacked it. So by the way, if you have any questions, remarks, advice during the presentation, don't hesitate to stop us. So let's introduce Switzer. Switzer exists since 2002, so that's a pretty long time for this kind of stuff. And AV companies still receive hundreds of new binaries daily. And if you see a Switzer binary, you cannot miss it because there are always some nice icons like these ones. And as far as we know, there are very little publicly available information on Switzer, and notably on the technical side of Switzer. So this presentation is going to be in 4 parts. I'm going to introduce the Switzer binary, and after that I'm going to talk about the packer itself, so the protection layer of the Switzer binaries, and the tools we built to attack this protection layer and understand it. And after that, Pierre-Marc is going to talk about the heart of Switzer, that is the original Switzer binary that is unpacked by the packer. And finally, we will talk about the men that are behind Switzer, and you are going to see that they are pretty strange. So let's introduce the Switzer binary. If you check a Switzer binary, you will see that it's a very standard Win32 binary, clean compiler signature, nice win main. There is always a long list of imports. It's also always statically linked with the C standard library. So that sounds pretty cool for an hardware. But if you try to open it in IDAPRO and dig deeper inside, you could see something like that. So you see that the main cone is running in the middle. And you can see that this code is calling a lot, there are a lot of calls to several small functions. Actually, these small functions are actually only doing some arithmetic calculations on their argument and returning back a result. So that's a very common scheme inside Switzer. So the small functions are probably automatically generated, and they are here to make the reverse engineering more difficult. So you could also see something like that in a function. So a lot of basic blocks, a lot of loops. So that seems pretty complicated at first. And finally, an over function. So these 3 screenshots come from the exact same binaries of Switzer. And this is the Switzer packer. So the Switzer packer, depending on the binary, but executes at least 40 million of CPU instructions. So that's a lot of instructions. And the objective of this packer is to protect the original code that I call the heart of Switzer, against reverse engineering and against detection by antivirus. So here is the problem. Our goal was really to try to build a kind of comprehensive understanding of what's happening inside Switzer. So both inside the packer, the protection layer, and the heart of Switzer, the original binary. But it seems pretty difficult at first. As we have seen, there are some wild stuff. And secondly, we are not hardcore reversers. We are pretty bad. So the first step was to deal with the packer. So let's set up the context of a packer. It's a monothread program with 32 bits binary, very standard. There is less than 1% of API calls. So it means that as our goal was really to understand, we cannot just check the API calls and just put breakpoints on the API and wait that something happens. We need really to think at the assembly level. And the third fact is that there is only one layer of code. Actually, the Switzer packer doesn't use dynamic code. There is no self-modifying code, etc. So the only dynamic layer is the original Switzer binary that is unpacked at the end. And finally, the fourth fact is that the packer layer for one Switzer binary will have exactly the same behavior over multiple executions. So there is no random stuff. Basically, if you run 100 times the Switzer packer for one binary, you have 100 times the same instructions that are executed, the same addresses, etc. And the more important part is that all the data access that are made in the data section of a binary still stay the same. So basically, the solution, this context is very Switzer specific. There is no random stuff, no dynamic stuff inside the packer. So the solution we built is based on this idea that there are a lot of information you can collect during one execution of one Switzer binary that are reusable to understand other executions of the same binary because they stay the same. The addresses stay the same, the data access stay the same. There is no dynamic stuff. So the set of tools we built was based on this idea. So first, we have a tracing engine, which is going to collect for us information. What kind of information? I'm going to explain that later. And secondly, we wanted to have some tools to exploit the collected information. So really here, the idea is that there is an enormous amount of information inside the Switzer packer, a lot of assembly instructions. So we wanted to have something that permits us to direct the standard reverse engineering work with standard tools and make it hopefully more efficient because of this context. So two kinds of tools we have developed. First, visualization tools, quickly identify interesting patterns, recognize already seen behaviors. And secondly, an heuristic engine, which basically helps us to rapidly diagnose already seen behavior. So really, to insist, here, the goal is not to build a new debugger, a new disassembler. We are happy with the current tools, or pretty happy. So the idea was there is a bunch of instructions, and we want to have something that permits us, for example, to divide the reverse engineering work in Asia subparts, provide us some attack points where we can begin to investigate the new binaries. So the work process is pretty simple. There are two steps. The first one is the tracing step. So we do it only one time per binary. So by the way, we don't really care about the speed of this trace, of this step, because until it is reasonable, we don't need necessarily to have a very fast tracing framework. Basically, we do it only one time for one binary. So the output of this tracing framework we are going to build are two files. So the first one is an improved trace. So by improved trace, we mean a very detailed view of what's happening during an execution. And the second output is an events file. So the events file is a more high-level view of what's happening during the execution. I'm gonna describe the improvement and the events which we detect. And secondly, there is the analysis step, which is the very standard reverse engineering step. But in this case, this reverse engineering task is really based on the previously collected information. So let's talk about the first part, the tracing engine. So like shown this morning, we use PIN. So that is the dynamic binary instrumentation framework supported by Intel. So basically, it permits you to insert arbitrary code written in C or C++ where you want inside your binary. PIN has a very rich library to manipulate your binary at different abstractions levels, so assembly instructions, basic blocks, library functions, etc. It deals with self-modifying code, so you can check it at this URL. So the question is, okay, we have PIN. What kind of information do we want to gather when we execute the Switzer packer? What are the interesting information? What kind of improvements we want in the trace? What kind of events we want to detect? And more generally, are they generic information that are interesting when you deal with such a packer? So the first kind of information we wanted to gather are the memory access. Switzer binaries have a big data section that contains a lot of weird stuff at first sight, and actually a part of this data section is already filled, and another part is going to be filled by the packer itself. So it will be interesting to see the access made by the code inside this data section, because as I told you, the addresses stay the same over multiple executions. So it's an interesting information to have. So that's very easy to do with PIN. Basically, PIN provides an API that permits you to know if an instruction is reads or writes the memory and how many bytes, etc. So I'm not gonna, that's one of the first example in the PIN documentation. So if you're interested, just check the documentation. So by the way, most of these access are not, or are pretty hard to decide statically because they use some register plus offset. They don't access directly with the address inside the data section. The second kind of information we wanted to detect or to collect are the API calls. As I told you at the beginning, there are not a lot of API calls inside the Switzer packer, and some of them are actually useless. But when they are useful API calls, that's cool to know because first, it gives good information. Knowing that the malware is calling load library, for example, that's interesting. And secondly, we don't care about the actual API code. We only care about the fact that the malware is calling an API function. If the malware called load library, I don't care about the code of load library. I only care about the malware code which is calling load library. So basically, by detecting the API function, from malware analysis point of view, I have a way to restrict my analysis to only the malware code. So PIN provides an API to deal with system calls but in the Windows world and for malware analysis, we only care about the high-level API function that actually perform the system calls. So how to detect API calls? There are two cases. The first one is when your API function is inside the dynamic linked library. So in this case, we use a pin function, which is this one, RTN find name by address. So basically, you pass to this function an address, and well, I don't know how is it really implemented as pin is closed source, but I assume they are passing the export table of the corresponding module and give you back the name of the function which is at this address. And if there is no function beginning at this address, they give you back a standard name. So basically, what we do where we are instrumenting the Switzer Packer, every time there is a call, we check if a called address has a name which is not a standard name. If it's the case, that's an API call. The second case of API call is when your function is inside a statically linked library. As I told you, Switzer is always linked with the C standard library. So that's interesting for us to know that the Switzer is calling strcmp. And so to do that, we need to know at this address there is strcmp inside the Switzer binary. So to do that, we use basically IDAFLOT, which is the IDA signature engine, and we just apply IDAFLOT on the Switzer binary, get back the result, and use the result inside our pin tool. So I don't know if I say that, but when you program with pin, you basically build a pin tool. A pin tool is just the name of the code you program. So we detect API call. It works pretty well, but we can do better. As we are dynamically monitoring the execution of the Switzer Packer, we can actually dump the arguments and the return values of the API functions. But to do that, the pin tool needs to know the function prototypes. So to do that, we give in entry to a pin tool a file. You have an example here. So this file is basically a formatted version of a standard C header file. So we basically just take the windows.h and stdio.h, etc., and make it in a formatted version like this. So at each line in this file, you have the return type of the function, the name of the function, the arguments type, plus a keyword, which is in, out, or out. So basically, when we detect a call to an API function, either dynamic or statically linked, we dump the in arguments, the in-out arguments, and after when we came back from the function, we dump the out arguments, the in-out arguments, and the return values. But to do that, the pin tool needs to know how to really dump the arguments based on the type. So in the same file, we give some instructions to the pin tool to make the type dumping. So basically, we divide the types in two flavors. The first one is the basic types. So for example, int is a D4. D4 stands for direct 4 bytes. So when the pin tool instruments a function and there is an argument to dump, if the argument is an int, it takes the argument as just a direct 4 bytes to dump. If it's a char star, it's a SA. SA stands for ANSI string. So in this case, the pin tool takes the argument as an address to a memory area, which is a C string, so terminated by a null byte with ANSI characters inside. And finally, if it's a PD word, it's a I4, so indirect 4 bytes. So it takes the argument as a pointer to a memory area of 4 bytes. So it dumps like this. And the second kind of types we have are the complex types. Complex types are basically either a composition of over types or just a pointer to another complex types. So for example, security attributes, which is a Windows Win32 type, is a composition of a D word, an LP void, and a bool. So when the pin tool has a security attributes to dump, it basically makes a recursive call to dump the first part as a D word, the second, etc. And the second kind of complex types, and the second example of complex types is the LP security attributes, which is just a pointer to a security attributes, indirect security attributes. That's it. So the third kind of events we want to detect in the Switzer Packer are the loops. So why is it interesting to detect loops in such a Packer? Because most of the time in this kind of Packer, a loop does one thing. A loop has one purpose. It's here to decrypt an area. It's here to resolve imports, to look for a specific function. It has one purpose. So if you adopt a divide and conquer approach, you can consider that all the code that is inside the loop is a kind of sub-problem that you can attack independently. All the code that is inside the loop has one purpose, so you can consider it as a sub-problem and attack it like a block. And moreover, there are a lot of loops inside the Switzer packer. So here is an example of 2 loops. You can see that they are using some call inside the loops. So basically, they play with the stack, and there are some instructions inside the loop that at each loop turn realign the stack. And moreover, there is more than 95% of the packer code which is inside the loop. So if we deal with loops, we basically deal with a big part of the packer code. So the question is how to detect loops. So it's very simple. At the left, we have a very simplified static point of view of a simple loop. And at the right, we have the pin tool point of view. So what is the pin tool point of view? It's basically the dynamic binary instrumentation point of view when you don't have any control flow graph, you don't have any knowledge of the future. So basically, you execute each instruction before each instruction. So when we execute this simple loop, there is obviously a repetition of instruction. Basically, when you execute a loop, you execute several times the same instructions. Okay, so but is a repetition of instruction always a loop? Obviously, no. If we take this simple example, so the same block of code composed of instruction 5 plus 6 is called as several paces, so take a function, and there is a repetition of instruction because this block of code is executed several times, and that's not a loop. So the question is, what is a loop? So a loop is defined by the package that comes between instruction 3 and instruction 1. So when you have a package, you have a loop. But we are in a very dynamic world, so what is a package from a dynamic point of view? If we detect the package, we detect the loops. So in the dynamic world, we define a package as an instruction pair composed of a leader instruction and a tail instruction. So the leader instruction has been first executed. So in the execution trace, you have the leader instruction first, and after that, you have a tail instruction that is executed just before the leader, at least 2 times. Why at least 2 times? Because if you do it only 1 time, you will detect the previous bad case of the same block of code called as several paces as a loop. So basically, the algorithm we have implemented in the pin tool detects at runtime the leader-tail pair. And so I'm not going to describe in detail the algorithm, but if you are interested, I'm very happy to share with you the code of the pseudocode. So it works pretty well. We detect all the Switzer loops. There are no false negatives. There are some limitations, but I'm not going to describe it. And it's the same idea that for the API calls. We detect loops, that's cool, but we can do better. We can actually gather some information about the loop. So the 2 main information we are collecting are the memory access made by the code that is inside the loop. So basically, we collect all the read access and the write access that are made by the instructions inside the body of the loop. So we collect this information as address intervals with a start address, end address. So, and basically, if there is 2 intervals that are adjacent, we fusion them. So at the end of the loops, we have, I'm going to show you some example. We have some big address interval and know, okay, this loop is reading here, writing here, etc. The 4th kind of events we are detecting is the exception. So why is it interesting to detect exceptions? Because basically, in a Switzer packer, you have at least 5 exceptions that are thrown deliberately. So at first, we were asking ourselves, what's the purpose of the exception? So to detect the exception, we basically just instrument the routine that is responsible to manage the exceptions on Windows XP, so KI user exception dispatcher. But always the same idea, we detect exception, that's cool, but we can do better. We can gather information dynamically, so we dump the error code of the exception and the fault address, that is the address of the instruction that is responsible for the exception. The 5 kind of event we are detecting is the dynamic code. As I told you, there is no dynamic code inside the packer. The only dynamic code is the unpacked Switzer binary, which is dynamically decrypted. So basically, we detect dynamic code as code executed outside the main module or shared libraries. So basically, at this time, we identify the instruction that transfers control to the unpacked binary. So it gives us an easy way to unpack Switzer because we have just to put a breakpoint on this instruction. The address is always the same, there's no problem. And after that, we have access to all the Switzer original binary. So finally, the last events we are detecting is the Switzer calculus. What we call a Switzer calculus is a small block of code, that makes some calculations on its argument and returns back a result. So remember one of the first slides I showed you, the small functions were so Switzer calculus. There are a lot of Switzer calculus in the Switzer packer. So there is no memory modification inside this kind of stuff, no API call, etc. So we detect them dynamically inside the pin tool with a very simple heuristic. Basically, if a basic block has between 7 and 20 instructions, more than 40% of arithmetic instructions, if it ends with a return instruction, we consider it to be a Switzer calculus. And by the way, we don't instrument the Switzer calculus. We don't follow the code because we don't care about the actual arithmetic operation that is made by the calculus. We store where the result is written because basically every time Switzer calls a calculus, the result is in the EAX register, and they always write the result in memory. So we store the address where the result is written because this address stays always the same. So that's interesting. So let's talk about the outputs. The first one, as I told you, is a kind of improved trace. So this trace is just a formatted file with different fields. So at each line, the first number is the time. So basically, the time is the number of instructions that are being executed. After that, we have the address of the instruction. After that, the assembly instructions, depending. And after that, the effect of the instruction, or the memory access. So R for read, W for write, and the address, the actual address of the memory access. So for example, at time 7, we had a call to an API function, open new tech. So we dump the arguments, we dump the return value. So A1 is first argument, type D word. This is the value, and etc. And we have the return value that is handled. At time 59, we have a call to a calculus. So basically, we name the calculus with an incremental counter. So we don't follow the code of the calculus. At time 93, we have a call to an API function, SNW printf. So basically, this function has an out argument, which is the first one, and is building a formatted string inside this argument. So you can see that the first argument is dumped at the end. It's A1, and that's the actual formatted string that is built by the call to this function. And at the end of the trace, we have an exception thrown by the previous executed instruction. So that's the first output. The way this trace is built helps us to make some, to look for specific regular expression inside. I'm going to show you an example after that. So the second output is an events file. So events file, the purpose of this view of this file is to give us a high-level view of what's happening. So basically, what we call events. So this is an example. For example, the first event is a calculus. We have the time of the call to the calculus, the address, the name of the calculus, where the result of the calculus is written. We have an API call, the time, the address, the name of the API function, the arguments. After that, we have a loop. So we have the start time of the loop, the end time of the loop, the lead address, the tail address, the number of turns, and the read and write zones. So you can see that there are some intervals with the length, the actual length of the interval. And finally, an exception, the time of the exception, the address, and the exception code. So in a standard Switzer packer, when we collect this kind of events, we have, depending on the binary, but we have at least 400 events for a Switzer packer. So that's not so easy to read in this kind of plain text file. So to make it more easier, we build a timeline, what we call a timeline, by using a widget made by the MIT, which is called Timeline. So basically, this widget is used to display historical timeline of events. And we just build a translator between our events file and the JavaScript code that is using the Timeline API to display the timeline. So I'm going to show you a video. So you can see the timeline here. So there are basically two bands. So the first one here, the top one, contains all the events we have detected. So the API calls, the calculus, the loops, the exceptions, etc. And the lower one here, actually this one has a big unit of time. And this one here, the lower one, has a bigger unit of time. So basically, the lower one permits us to rapidly navigate through the timeline. I'm going to show you an example. So if I launch the video, yep. So that's interactive. We can click on the events, get the arguments. For example, for an API call, we can drag the timeline. We have the loops. So you can see that there are some imbricated loops. We have the read zone, write zone, etc. So the lower bound permits us to rapidly navigate. We drag it. So when we click on the events, we have the collected information associated with the events, so the load library, for example. So if I come back to the start, we can do some funny things like, if we take, for example, the return value of get command line, that is the name of a binary, we can highlight it. So I take the name of a binary, I put it in highlights, and I have all the API calls that are actually using the name of a binary as an argument. So for example, here they are looking for a specific character inside the name of a binary. We can make some filters. So for example, if I want just to display the API calls, I put API. If I want to display only the loops, I put loop. And finally, we have also a way to not display certain events, some events. So for example, I want to not display the calculus. Okay, so I have everything else. So that's pretty basic at this time, but it helps us a lot during the reverse engineering process because it gives a big picture of what's happening during the execution of a Packer. And so you can basically know where you are and rapidly diagnosis, okay, this is an already seen behaviors, I've already seen this stuff, etc., etc. So that was the tools. So what about the actual Switzer Packer? So I'm going to describe the Switzer Packer as some eras. So what I call an era is just a period of time that has one purpose. So the first era, the era 0, inside the Switzer Packer, inside all the Switzer Packers, actually, you can see that there are some interesting API calls. So for example, there are several calls to SNW printf, to the function that build a formatted string. So why are they building formatted string? So they are playing with a mutex. You can see at the beginning there is a create mutex at the bottom. So, and there is also, they are looking for an argument inside the name of a binary. So they are really looking for the argument. And there are some mallocs, but actually all these API calls are totally useless. It's very easy to check. If you take the malloc here, we can just check inside the trace if there is any read or write access to the allocated memory. And you can see that there are no results. Basically, nobody is using this allocated memory. And that's the same for all these API calls. If we take, we can very easily check this by using the trace plus regular expression. Nobody is using the result of the SNW printf, etc., etc. So the only purpose of this era is to use the calculus. And the calculus has used, you can see that there are a lot of calculus are used to feed some structures that are going to be used by the next eras. So the next eras is really the preparation step for a Packer. Basically, it decrypts all the structures that are going to be used by the Packer, patch table, etc. So there are a lot of loops inside this era. So let's take an example of a very simple loop. Actually, there are two loops. There are loop 1 and loop 2. You can see that loop 1 is beginning just before loop 2. So basically, loop 1 contains loop 2. And there are some pretty weird stuff if you see the read zone and the write zones. So for example, the loop 2, inside the loop 2, the read zones and the write zones, there are some zones that have been exactly read and write, the same exact zones. And there is a big zone that have been only be read. And if you check the loop 1, there are a lot of small read zones and write zones, and two big two 16 bytes read zones. So the question is, why is it like this? So at this time, it's really, we need to do some standard reverse engineering by using standard tools. But first, we wanted to have a more precise view of what's happening inside the memory. So we developed another visualization that is also very basic. We call it memory profile. Basically, in this view, each byte of the data section of the Switzer binary has an associated profile. So what is a profile? A profile is the number of times this particular byte has been read, written, or the target of a call or jump. So basically, we take the trace and compute the memory profile for a specific period of time. And we display it. So we attribute a color. We have 3 numbers for each byte. And we attribute a color depending on the 3 numbers. So it's done in an interactive manner. So when we click on a byte, we have the address and the associated profile. So we use Python plus matplotlib to do that. And so the question is, okay, why is it interesting to have this? Basically, this view is totally independent from the code. We don't have any assembly code here. We only have the access made by the code. We only have the memory access made by the code. We don't play with assembly here. So I'm going to explain you why is it so useful. So if we, at this time, we do some standard reverse engineering to understand the loop. And so our goal was to understand what's happening inside the memory. So if we take this bunch of bytes, you can see that all these bytes, they are adjacent and they have been read by the code. And there is something weird. The first bytes have been read 5 times, after that 3 times, after that 2 times, and finally 1 time. So why is it like this? So we do some reverse engineering. Basically, the way the algorithm, that's an decryption algorithm, and the way it works, it decrypts several areas of different length with the same key. So basically, every time the algorithm begins to decrypt a new area, it begins to scan the key from the beginning. So for example, if the smallest decrypted area is 2 bytes length, the 2 first bytes of the key are going to be read 1 more time than the 3rd byte, because the 3rd byte is not used to decrypt this smallest area. So it's why we have this decreasing profile, because they always begin to scan the key from the beginning when they decrypt a new area. So that's the key. We also have some two structures that have been only read. And these 2 structures are actually control structures. They basically store all the addresses of the decrypted area and the size of the decrypted area. So their length is basically the number of decrypted area by 4. So these are the control structures of the algorithm. And finally, we have here 4 areas that have been read and written. So basically, that's the decrypted areas. They read it, they make some calculations, and after that, they write the result. So we should have 5 decrypted areas, but the other one was in another place inside memory that was not really nice to display it. So here are the decrypted areas. So once we have understood that, what we can do is that basically we use this memory profile that is completely independent from the code, and that's only the effect of the code inside the memory. And we use this view to develop some heuristics only on this view. And basically, the heuristics use what I just told you, the fact that the key has a decreasing profile, the fact that the control structures have a specified length, the fact that the decrypted areas have been read and written. So we develop some heuristics just based on this memory profile. And that's pretty useful because in Switzer, that's very common that the same algorithm is implemented several times and they use some syntactic obfuscation. So it doesn't look the same, but it's actually the same. And by having the heuristics only on the memory, we don't care about the syntactic obfuscation. So basically, we just have a small engine, which is we give to him the start time of the loops, the end time, and it checks if he computes the memory profile, and it checks if it has already, for example, if it's probably a key, if there is probably a decrypted area, if there is a possible control structures. And it works pretty well because of this fact that in Switzer, the algorithm, there are not a lot of different algorithms, but there are a lot of different implementation of the algorithm. So let's take, in the same era, a more original loop. So if you check the read zones and the write zones by this loop, you can see that there is not a big read zone, but there are actually a lot of small read zones. And between these small read zones, of 8 bytes, there are always 3 bytes. So they basically jump over 3 bytes. They read 8 bytes, they jump over 3 bytes, etc. And at the end, we have a big write zones. So if we check the memory profile, you can see that there is a nice pattern due to the fact that they jump over 3 bytes. And so there is this big write zone. So at this time, we do some standard reverse engineering to understand what's happening. So here is the code. So that's pretty simple. So we basically just reverse it and understand what's happening. But if we check these over loops in the same binary, So basically, there are a lot of basic blocks, a lot more of instructions, and so it seems more complicated. And if we check just the read zones and the write zones, you can see that that's the exact same situation. But in this case, they jump over 2 bytes, but that's the exact same characteristics. So basically, that's the same algorithm implemented in more complicated manner and just jumping over 2 bytes. So in this case, when we are reversing such loops, most of the time, we only care about the decrypted area. Basically, the way we attack loops is, okay, we check the read zones, the write zones. Is it something I have already seen? If it's the case, I apply the heuristics I have, or I just check the decrypted areas if I know that's just a decrypting loop, etc., etc. If I don't know the shape of the read zone and write zones, I do some standard reverse engineering, try to develop some heuristics only based on the memory profile to permit me to recognize the same behavior after that. So let's enter the era 2. So remember one of the first slides I showed you of this function. So if we take a closer look at the beginning of a function, we have something like that. So basically, this function takes in entry a big bunch of data. Actually, these data are counter. Basically, the function takes the first 4 bytes of this data and add them with themselves. And after the addition, it checks if the result is 0 or no. So it gives 2 possible paths, 0 or no, not 0. And after that, it checks if the result of the previous addition has overflowed or not. So if the curly flag is set to 1 or not. So basically, and after that, it remakes an addition with the previous result. Actually, if the result of an addition is 0, they take the next 4 bytes in the data area. So basically, it has the shape of a binary tree. At each node, you have 2 possible paths. You make an addition, you have 2 possible paths, etc., etc. So that's exactly a binary tree, but that's not a binary tree because at certain point inside the tree, there are some loops, so that's no more a tree. Basically, if we have a high-level view, you can see that at the beginning, it begins to have the shape of a tree, but after that, the block in purple are actually some loops inside the tree, and these loops are actually responsible to calculate a single byte. So each of these loops calculates a single byte. And this single byte is actually the decrypted byte, the byte that is going to be read, that is going to be write in the decrypted area. So this function is just a decrypted a function that decrypts an area. And the funny thing is that this function is present 3 times in every switch or packer, but the 3 times the implementation differs. And one time the function is here to decrypt the data section, after that the R data section, after that the code section of the original switch or binary. So these are really the last loops that are executed by the switch or packers, and they basically serve to decrypt the 3 main sections of the switch or binary, original switch or binary. So as I'm running out of time, I'm not going to say that. So basically, as the unpacked switch or binary is normally mapped at the normal standard address, they need to patch all the absolute address. So there are big patch tables inside switch or packers to modify the absolute address because they are now in dynamic memory. I have some, just to let some funny things about the packer. They check the Canal 32 timestamp against the Windows 95 Explorer.exe timestamp. So if it's closed, the program exits. And they have some anti-emulation tricks. They check the first 4 bytes of RTL decode pointer. If it's a very particular value, they exit. So we are sure that it's an anti-emulation trick against a specific AV. And they look for functions inside export tables, import tables. So the original thing is that they use the import tables of certain modules to look for function in other module, and they don't look directly in the export table of the first module. So that's it with the packer. Let's talk about the original switch or binary.
Hi, can you guys hear me okay? Okay. So I understand most of you must really hate me right now because I'm the only thing standing between a cold beer. So I will try to make this as painless as possible because I also like cold beer. I have for about another 15 minutes of presentation. So once we were able to understand the obfuscation scheme used by Switzer, the next step was to actually look at the unpacked code and find out what it is doing. Because it's nice to develop some kick-ass tools, but it's even better to apply them to a real problem and find interesting things. What we had to do was to look at millions of different files, and we wanted to understand what they do. It was interesting to find out that they had many common characteristics, which I'm going to describe a bit later. Interestingly, the Switzer obfuscation scheme only seems to have been used by the same gang, the same group of people, because when you look at the unpacked code, it has many, many things that lead me to think that the programmer were the same people. The first thing we had to do with Switzer was actually to understand where the files were coming from and how they were related one to another, because we had so many of them. So in a typical scenario, Switzer would be installed on a machine by a dropper. This dropper is a third-party application. Switzer is an adware program, so the dropper would be some other application that would use it as a sponsor program. So the dropper would be in charge of two things. First, it creates some registry entries and stores some key information in there. For example, you will have the affiliate ID for the guys to claim money at the end of the day, and some software version. The dropper then launches the updater. This updater will register as a system service and will continuously run in the background, frequently checking for updates and installing them. So the first time the updater is launched, it will download a second stage binary, which will be in charge of delivering advertisement. And the second stage binary will be different according to the affiliate ID. Interestingly, all these different components are interrelated, and they will not usually run by themselves unless they have been started by their related components. The way it's done is that these binaries will check for their command line arguments, and if they don't find the value they are looking for, they will simply exit. So if you don't have any view of the unpacked code, finding these relations is quite hard. One of the common characteristics that we found inside Switzer is that they are using code injection. From what I understand, there are two main reasons for that. The first one is to make reverse engineering even harder, and the second one is to bypass any firewall rules that would, for example, block internet access to unknown applications. So what Switzer would do is that it will inject its code inside Internet Explorer. And then the original binary will check if it is actually running inside Internet Explorer. If it is not, it will start Internet Explorer, write its original binary inside the Internet Explorer, patch its own process, and start again. So what I did is that I started playing with the thing. After a couple of days, you end up understanding, oh, okay, it's doing code injection. Let me try to follow this code. Then I was able to follow the code. And then I was just back at the beginning of the whole process because it's the same binary running inside Internet Explorer. So what was really important was to find the place that was doing the check to see if the binary was running inside the Internet Explorer or not. And the way it would do it would be to check the registry value and look at the registry and find the path to Internet Explorer. And once it has this path, it will search for the file name of the binary that is running. If these things are different, then it will inject inside Internet Explorer. So if you are able to find this check inside Switzer and simply patch the jump, then you can execute the original binary without having it inject itself inside Internet Explorer. Another interesting characteristics of all the Switzer files I've had to look at is that all the strings inside the binaries are encrypted. They are using a very basic algorithm, which is to XOR strings. And once a string is needed by the binary, by the execution flow, it will be decrypted on the fly, meaning that if you are able to dump the memory of some process, you will not find many strings in clear text. The interesting characteristic of this algorithm is that the first two characters of an encrypted string will be the index in where to start in the key for decryption, meaning that you can generate 120 different strings with the same plain text input. The limitation to this algorithm is that it is also used to encrypt network communication, meaning that both the server and the client need to know the key. And that means that the key cannot change very often in the binary. So after reversing a couple of the different binaries, we found out that the key is always the same. So you can quickly write a Python script that is going to decrypt the strings you see go by and understand lots of interesting things. So here's a quick example up there of the encrypted string and then its decoded value. Now, as I told you, Switzer, the main purpose of this whole thing is to deliver advertisement. So the adware delivery mechanism will frequently check on an update server, sending information like the number of active windows inside on the PC, the time, the amount of time it has been running. So when you launch Switzer, you will not see any advertisement for a while. It will check in, but it won't display anything until it reaches a certain value of time running, of active windows, etc., etc. And then you will receive all kinds of fun advertisement. Where this one is for Rogue Antivirus. The updater is responsible for fetching different bundles to install on an infected PC. The problem is that the updater is very generic, and it contains information about all the affiliate IDs. It will actually, it has a nice function, on which you can see on the right, which is a big select case. It takes as input an affiliate ID, and it outputs the path on the server to find some update. So if you are able to decrypt the strings inside Switzer binaries, you can actually find all the files that they are using for their different affiliates. The reason they are using a format string up there is that they are also randomly generating domain names or host names, so that it's harder to blacklist completely these things from the network perspective. The last interesting characteristic of these Switzer binaries is that when they start, they will first look at the host file on the Windows system and try to find any entries that would be used to blacklist some domains. And it checks every domain located in the host file against its internal list, and if there is a match, it will remove the blacklisting from the host file. This was really, really interesting to us because it gives us a complete list of domains used by these guys. Which leads us to the last part of this presentation. Thank you for holding on until now. Dark connections. So we wanted to call this section the folklore part of this presentation because it's just interesting stuff that we found while reversing Switzer. So you don't necessarily believe everything you see here. Use your judgment, please. So Switzer seems to be maintained and developed by a company called C2 Media, or LUP. I'm not sure which one is which because these guys seem to be changing names very often. What seems very obvious to me is that they make their money through advertisement, either via pop-ups, installing toolbars, and also through advertisement on search engines. Each and every piece of software created by this company is using Switzer type obfuscation. They even have an uninstaller on their website that allows you to uninstall Switzer, but it's actually packed with Switzer. So if you upload this file to VirusTotal, it's detected by 30 out of 40 AVs as being malicious. There seems to be tons of companies involved with C2 Media. Some of them are owned or directed by the same people. For example, Trinity Acquisitions, LUP, CID. I'm only giving you the names here if you want to search for them later. And then you have companies which seem to be collaborating with them. For example, WakeNet, which is offering money for install. And also, for a long time, Messenger Plus, which is a popular add-on to the instant messenger from Microsoft, was using LUP or C2 Media's Switzer to fund their programming. By looking at the different host names that we found, and then looking at the domain information, the IP space that these guys were using, we found 3 names that were coming repeatedly. The first of which is Jason Lucas. He usually goes by the nickname Trinity. He is probably based in Florida. He seems to be the director of C2 Media and other companies like CID and Trinity Acquisitions. What's really funny about this guy is that there are many rumors about him. There are tons of rumors. Many people say that he is a pro in psychology operations, and he would also be involved with some new training facilities for the American Army, making them superhuman or something. Another name that comes up really often is actually a nickname, Pachu. He is the actual maintainer of Messenger Plus and the main programmer. He received a Microsoft MVP award, but then Microsoft retracted after a day or two because they found that, that his software was also used to distribute hardware. He is the owner of different companies like Yuna Software and Kimari Software, and he's actually based in Montreal, and they are hiring some C++ developers right now. The third guy is a bit more shady. I don't have much information about him. He is called Alex Shamash, probably based in the UK, and the owner of a company called Secure Software. And it is my intuition that he might be the developer's connection, the guy at the head of the developers of Switzer, but this still has to be proven. Now, when looking at all these guys, we started digging some stuff up, and one of the really funny stories was about Godlike Productions. It's a forum to discuss conspiracy theories, and it was allegedly bought by Jason Lucas. So the guys on the forum were not really happy that their forum had been bought by a spyware or adware or evil guy. So they started talking about it and complaining about it. And it appears that Jason Lucas started editing the posts that were made to this forum, changing keywords. For example, he would change lop.com to bunny, and then spyware to flower. So many people thought that since Jason Lucas is a kingpin in psychology operations, he was actually controlling their brain. He might have also been replacing words in their database, but who knows? So that's it. Just imagine the situation. You start reverse engineering something, you really have no idea how it is going to end up, and a couple months later, you end up on a forum reading about bunnies and flowers. It was quite an interesting experience. So to sum up, we had a quite complex target, which was Switzer, millions of files. We didn't know what they were doing. So our approach was to create a tracer that would provide as much information as possible, and then some visualization tool to help us process this information and improve our reverse engineering. And the conclusion was that we had lots of fun. So thank you very much.